Good evening, all. I welcome you all for the Week 10 live interactive session for the course Chemical Reaction Engineering 2. Now, let's get on to the session. So, let's have a brief recap of lectures of Week 11. So, Week 11 was mainly based on the residence time distribution. It had 5 lectures, where the first 2 lectures were on. Hello, Sandhya, you are able to hear me? Can you please unmute and speak? Or if you're not able to speak, can you just type in the chat box if you are able to hear me? Okay, anyway, let's proceed with the recap of this week 11. Uh, so, week 11 had 5 lectures, of which all the lectures were based on the residence time distribution. The first 2 lectures were on measurement of RTD, residence time distribution. So, in lecture 51, the discussion included tracer injection methods, where 2 major type of tracer injection for identification of the residence time distribution function was discussed. One was the pulse input, the other one was the step input. Further into the session, the pulse input was described in detail, where a single input and single output system was discussed. Here again, the C curve, the definition of RTD function, and the limitations of a pulse input were all discussed in the session. The next lecture was on continuation of measurement of RTD, and this lecture included steps to find E curve in the case of pulse input, and then this was followed by a discussion on step input, where the E curve and F curve were discussed, and some of the pros and cons of the step input were also discussed. And then this was followed by discussion on other tracer techniques like negative step, and then frequency response method, and then inputs different than that of a pulse and step were all discussed. And then the definition of the f of t, which is the cumulative function, which is nothing but the f of t gives the fraction of effluent that resided in the vessel for time less than t. The expression is given by integral over 0 to t e of t dt, where e of t is nothing but your residence time distribution or your E curve. And lecture 53 was on RTD functions, where different parameters like mean residence time, and then variance, that is the second moment, and skewness, that is the third moment, were all discussed. And no, normalized residence time distribution function was discussed, where time in the normalized form or the dimensionless time form was T by tau. And there was a discussion on internal age distribution. Lecture 54 was on properties of RTD functions, where RTDs for ideal reactors such as PFR, single CSTR. PFR is nothing but your plug flow reactor, and then single CSTR, and then a laminar flow reactor were all discussed. Here again, what is the E curve, F curve, expression for the residence time distribution, and then expression for F, and then variance, and then what is the expression for mean residence time were all discussed. And in each of these cases, the mean residence time, under the condition that there is no dispersion, is equal to the space-time tau. Uh, and the final lecture for the week was on reactor diagnostics and troubleshooting. So in this lecture, there was a continuation on discussion on laminar flow reactor, and then the RTD diagnostics and troubleshooting was introduced, where common RTDs, that is the residence time distribution function for common reactors like a plug flow reactor, and then CSTR, and then packed bed reactor, were all discussed. Now, let's get on to the week 10 practice assignment session. Question number 1. Identify the reactors for the following E curves. So, there are 3 different E curves given, where in the case 1, there is a skewed E curve with a long tail, and your space time is somewhere in between, as shown in this figure. And in B, the E curve is having 2 peaks, where the tau is just before the second peak. And then in figure C, there is a E curve that is given, which is having a spike, or just a straight line of infinite length, where this line is at t equal to tau. So now we have to identify the reactors having such E curves. So let us see each of the case. Case 1, it is for the case of a tank reactor or a stirred tank reactor with channeling or bypassing and then dead zones. So if we look into this figure, we can see that this reactor is having, this is a stirred tank reactor, where some of the input stream is just bypassing without getting mixed or interacting, and it is just getting channeled and getting escaped. Whereas there are dead zones, as we can observe here, which takes a long time, which occupies the reactor for a long time, and this is what is shown in this E of t curve. So if you look into this E of t curve, the first spike or the peak represents the bypassing. So those fluid particles which are bypassing will exit the reactor at a very short time compared to that of your space time, okay, or your mean residence time. It's actually, the tau is nothing but a space time, okay, where space time is given by volume of the reactor divided by the volumetric flow rate, considering the volumetric flow rate to be constant. Okay, so this initial peak, which is very close to 0, it corresponds to the bypassing, whereas a long tail, it represents the dead zone. That means the material in the dead zone takes a very long time to come out of the reactor, and that is what is projected in terms of the excitage having a long tail here after the tau. Okay, so this is, so the first figure corresponds to a tank reactor with channeling or bypassing and dead zones. Okay, what about the figure 2? Figure 2 represents a packed bed reactor, here again, which is having channeling and dead zones. So in the case of packed bed reactor, here again, what happens when there are channels, okay, between the particles? So packed bed reactor, we know that it is packed with either catalyst particles or some particles. Okay, so what happens, since there are particles packed, so there may be a certain area where you might not find the intensity of particles, and there is very less restriction for the fluid to pass, so it easily passes through the reactor, such that it passes out of the reactor well in before the space time. Okay, so that is what is represented by the first peak, which is well before the space time tau. So this represents, the first peak represents the channeling, whereas Here again in these reactors there are dead zones where the fluid finds lot of restrictions because of a lot of particles in that particular area. Okay, so due to the non-uniformity in packing. Okay, so what happens, so that fluid takes a very long time compared to that of the space time of the reactor, and it takes a longer time to come out, which is shown by the second peak. Okay, so this is what is the uh, second peak represents in the figure 2. So thus the figure 2 is the exit age distribution curve for a packed bed reactor with channeling and dead zones. What about the third figure, which is having a spike? So this corresponds to a ideal PFR. That means all the atoms, it has the same residence time. That is why we could see an input of the tracer inlet with a spike at t equal to 0, uh, having a length of infinity, and uh, the same peak could be, the spike could be seen for the output at time t equal to tau. That means at the space time of the reactor all the particles uniformly come out, and that is why we observe a spike, and this is actually represented by a direct delta function. So where the area under the curve is 1, and the uh, you know and it occupies a infinite length, while it is a in the x-axis it is just a single spike line. Okay, now let's move on to question number 2. Question number 2. The variance for an ideal PFR is dash, while for an ideal CSTR is dash. So variance, we know it is the second moment. Sorry, it's the second moment. First moment is your residence time. Second moment is your variance, that is sigma square. And sigma is nothing but your standard deviation. Okay, so what is the variance for a PFR and what is the variance for an ideal CSTR? The answer is, the variance for a ideal PFR is 0. So because we saw in it is a direct delta function, and if you find the second moment of this function, you will find that the value is equal to 0. That means there is no variance, or because all the particles are having the same residence time, so the variance in data is 0. That is why the variance for a ideal PFR is 0. What happens in the case of CSTR? In the case of CSTR, the variance is equal to square of the space time, that is the tau. Okay, now let's move on to question number 3. The concentration readings in the below table represents a continuous response to a pulse input in a closed vessel, which is to be used as a chemical reactor. Calculate the mean residence time of the fluid in the vessel and tabulate and plot the exit age or the residence time distribution. Okay, now what are we supposed to do? So they have given some data where they have given time in minutes and the tracer output concentration for a pulse input. So time is given in minutes and the tracer output concentration is given in gram per liter. So we have time as 0, 5, 10, 15, 20, 25, 30, 35. So up to 35 minutes the data is given for every 5 minutes. And the concentration of the pulse tracer is, the input tracer is a pulse tracer that is being given to the reactor. Okay, and the output concentration of that tracer is given for the given set of times. Okay, so initially at time t equal to 0 it is 0, whereas at 5 minutes it's 3 gram per liter, 10 minutes it is 5, 15 minutes it's again 5, and 20 minutes it's 4, and 25 minutes it is 2, and 30 minutes it's 1, and again at 35 minutes it goes to 0. So now what are we supposed to find? We are supposed to find the mean residence time, that is the first moment, and also the exit age distribution, that is E of t curve. We have to find out the values of E of t and also plot the curve, plot the E curve. So how are we supposed to do this? Now the solution is, we know that E of t is nothing but your C of t divided by integral 0 to infinity C of t dt. So this can also be written in another form as C of t by summation of C of t delta t from time t equal to 0 to infinity. Since we have discrete points, again instead of integral we are just using the summation. Similarly, we have to find the mean residence time. Your mean residence time is given by integral 0 to infinity t into E of t dt divided by integral 0 to infinity E of t dt. So, which again can be written in terms of summation, where Tm is equal to summation over 0 to infinity t into E of t into delta t divided by summation of E of t into delta t. So, we know that integral 0 to infinity E of t dt, the area under the E of t exit age distribution curve over the entire time span of 0 to infinity is nothing but equal to 1. So, your Tm, your mean residence time, becomes summation over the time 0 to infinity t into E of t into delta t. So, now we have to find out their individual values. So we have the table with all of these. So we have been given time and pressure output concentration in gram per liter. Now we can find from this what is delta T. So we can find out delta T for each case. So delta T, time difference between T1 and T0 is 5. Similarly, T2 and T1 is again 5. Similarly, T3 minus T2 is again 5. So, for all the cases, the time is actually uniformly distributed. That means your delta T for all the cases is 5 minutes. Okay. Now, we can find out what is C into delta T for each case. So, for the first case, it is 5 into 3, that is nothing but 15. So, we have to, mention the unit also. C delta T is nothing but gram minute per liter. Okay, because C is in gram per liter and time is in minute, so it is gram minute per liter. Okay, so C delta T for first one is 15, then 20, 5 into 5, 25. For the third case, it is 5 into 5 again 25. For the fourth, it is 4 into 5, 20. And for the fifth, it is 2 into 5, 10. And the next one, it is 1 into 5, 5. And the last one, it is 0 into 5, 0. Okay, and the summation of all these things is 100. So from this, we can also find out what is E of t. So E of t is C of t divided by summation over 0 to infinity C of t into delta t. So the summation of C of t delta t, we know it is 100. So E of t for the each cases, it is first, so at time t equal to 0, it is 0 by 100, that is 0. Then t equal to 5, it is 3 by 100, 0.03. And at time 10 minutes, it is 5 divided by 100, 0.05. And the next one, it is again 0.05. Next 0.4, 0.04 and 0.02, 0.01 and 0. Okay. So, we have got the values for E of t, right? So, from this we have E of t and time. So, we can just plot it. So, you will get some curve like this, kind of bell-shaped curve, but there is slight skewness towards this side. Okay. So, this is what is the E curve. So, they have asked us to find out the E of t at all time points and also plot the E curve. That is what we have done in this case. Okay. Now, what else we have to find? We have to find out the mean residence time. So, for finding out mean residence time, we have already seen that it is nothing but your summation of t into E of t into delta t. So, we can find out what is E of t into delta t. So, we just have to multiply this column with this column, the E values with delta t, you will get E delta t. What is the value of E delta t? Okay. So summation of E delta t will be equal to 1. So that is what we have seen here also. Integral over 0 to infinity E of t dt is nothing but equal to summation of E of t into delta t, which is equal to 1. Okay. This can be kind of a cross checking if it is the uh, the area under this curve is 1 or not. So if we get 1, then it's right, it's 1. Okay. Next we have to find out what is mean residence time. Mean residence time is given by summation of t into E of t into delta t. So we already have for each time points what is E into delta t. So we just have to multiply time for each of these. So it is 0 into 0. For the first one at time equal to 0, it is 0. For the second case, it is 5 into 0.15, 0.75. The third case, it is uh, 10 into 0.25, which is nothing but 2.5. Third case, 15 into 2.25, which is 3.75. Fourth case, it is 20 into 0.2, that is 4. We are just multiplying the values in this column with the time. So we'll get these values of 0, 0.75, 2.5, 3.75, 4, 2.5, 1.50. And the summation of this is 15. That means from the table we can find out the mean residence time is 15 minutes. So for this case, for the given set of data, the mean residence time is 15 minutes. Okay. Now let's go on to question number 4. In a laminar flow reactor with a parabolic velocity profile, E of t is equal to tau square by 2t cube is it valid for t from 0 to infinity, or is it valid for t less than tau by 2, or is it valid for t greater than or equal to tau by 2, or is it valid for t between 0 to tau. So for which of these cases, in the case of a laminar flow reactor, having a parabolic velocity profile, the E of t equal to tau square by 2t cube is valid. So we know that in it is a laminar flow reactor. So the laminar flow reactor, it is also, they have given that it is having a parabolic velocity profile. That means the velocity of the particles at the center at r equal to 0 is maximum, whereas the velocity closer to surface, that is at r equal to r is minimum or 0. Okay. Due to the slip conditions. And that means the particles that are moving at the center, that is at r equal to 0, will have maximum velocity. That means that will have mean residence time. So if we substitute that into the velocity profile, we will find out that the time taken for it is not mean residence time, it takes the minimum time for the exit. So if we substitute that into the time taken for the minimum time taken by the particles in the center of the laminar flow reactor, which is having the maximum velocity, the time taken for it to exit the reactor will be equal to tau by 2. So this expression will be valid only if your t is greater than or equal to tau by 2. So because the particles having the maximum velocity itself requires a time of tau by 2 to come out of the reactor. That means any other particle in any other plane at any other r will require a time greater than tau by 2 to come out of the reactor. So the exit age for those particles will be greater than or equal to tau by 2, and that is why your E of t is valid. E of t equal to tau square by 2 t cube is valid when your t is greater than or equal to tau by 2. When t is less than tau by 2, then the exit age distribution E of t is equal to 0. That means none of the particle can come out, because the particle with the maximum velocity needs a time of tau by 2 to come out of the reactor. That means only after tau by 2 only you will start finding the particles coming out of the reactor. So this is what it actually means. Okay. Now let's go on to question number 5. Internal age distribution is related to exit age distribution. So in the lectures we have covered through the concept of internal age distribution and exit age distribution. So here exit age distribution, it represents the age of the fluid leaving the reactor, whereas your internal age distribution, I of alpha, it represents the age of the fluid that is actually present in the reactor between alpha and alpha plus d alpha. Okay, so yeah, there is a relation. There must be definitely a relation between the internal age distribution and the exit age distribution. So what is that relation? So is it I of alpha is equal to 1 by tau into 1 minus of integral 0 to alpha E of alpha d alpha, or is it B I of alpha is equal to 1 by tau into 1 minus E of alpha into d alpha, or is it C I of alpha is equal to 1 by tau into E of alpha into d alpha, or is it D I of alpha is equal to E of alpha? So which of these is the correct relationship? So the answer for this is, it is actually option A, which is I of alpha is equal to 1 minus, I of alpha is equal to 1 by tau into 1 minus of integral 0 to alpha E of alpha into d alpha. This is how the internal age distribution and the exit age distribution are related. Now, let's go on to question number 6. A CSTR has a long inlet pipe. A tracer is injected at the entrance of the pipe. The exit age distribution curve obtained at the exit of the CSTR is shown in figure below. This is what is the exit age distribution of the CSTR. Assuming a plug flow in the inlet pipe, the ratio of volume of the pipe to the volume of the CSTR is, what is the ratio of volume of the pipe to the volume of CSTR in this case? So this is a GATE 2016 question. So what have they given? They have given that there is a CSTR which is also having a long inlet pipe, and a particular tracer is injected at the entrance of this inlet pipe. Okay, and they have given the exit age distribution curve for this CSTR having a long inlet pipe. They have asked, and they have also given an additional information that the flow in the inlet pipe is a plug flow. And they have asked us to find out what is the volume of the pipe to that of the CSTR. So we have also been given a E curve, which is having a zero value from 0 to 5 minutes, where they were, and then a spike at 5th minute, and then we have a exponential decay curve up to 80 minutes. Okay, now how to proceed with this problem? Now the solution is, sorry, okay, let's proceed. So the E curve for the pipe. So first we have to find out the E curve for the pipe also, because there is the pipe is quite long, and the fluid has to enter and exit the pipe also in order to enter into the CSTR. That means the fluid will have its own residence time inside the pipe also. One additional information what it has been given is that the flow in the pipe, inlet pipe, is a plug flow. That means all the fluid particles will have the same residence time, will come out of the pipe at the same time. So it will have a spike. So that is nothing but this spike which you can see at time of 5 minutes. So With this, we can find out the E curve for the pipe, which is nothing but E of t for the pipe is nothing but your direct delta function given by delta of t minus tau p, where tau p is the space time for this pipe. Okay, so this part of the curve is nothing but your spike according to the plug flow for the inlet pipe. That is why we are able to see the spike since it is a plug flow. Okay, and it is a direct delta function, and tau p is nothing but, because for a ideal PFR we have seen that your E of t curve is a direct delta function, right? We have seen in the question number 1, right? It is a direct delta function with a spike at time equal to tau, right? So in this case, what do we observe? We observe a spike at time equal to 5 minutes, right? Till 0 to 5 minutes it is 0, and then a spike at time equal to 5 minutes, right? That means this is the E curve for the pipe with tau equal to 5 minutes, tau p equal to 5 minutes. Okay, now so we have from the plot we can find out that your tau p is 5 minutes. So your tau p is nothing but your volume volume of the pipe divided by volumetric flow rate V naught. Okay, next step is, now what is the exit age distribution for the CSTR. So in general, the exit age distribution for a CSTR is nothing but a exponential decay curve, which is given by exponential of minus t by tau, the whole divided by tau, right? Now in this case we have a CSTR with a long inlet pipe, right? That means the material has to flow through the inlet pipe and then through the CSTR. That means we can observe that the exponential decay curve starts after 5 minutes only, right? After this only you can find the exponential decay. So this is the time it has to pass through the inlet pipe. So we have to account for this condition in the expression of the exit age distribution curve in CSTR. That means whatever time points we are getting, it will have a time lag of 5 minutes, right? Because it has to flow through the pipe for the first 5 minutes and then flow through the CSTR for the remaining time, right? So your exit age distribution curve expression for this CSTR having a long inlet pipe is exponential of minus t minus tau p divided by tau of CSTR. Tau of CSTR alone, the whole divided by tau of CSTR. Here we mentioned t minus tau p in order to account for the fact that the material will start coming out of the CSTR only after a time lag of 5 minutes, because it has to first pass through the inlet pipe and then through the CSTR and then come out of that. That is why we are including an expression of minus tau p. Okay. Now we already have the value of tau p to be 5, right? Now how to find out the tau of CSTR? Let's proceed. Here from the plot of E of t, it can be observed that the exponential decay curve for CSTR starts from after t equal to 5 minutes, that we have discussed. Okay, and we have seen the expression also. At t equal to 5 minutes, the E of t value is 0.05 minute inverse, right? So in this figure we could see that at t equal to 5, your E of t value is nothing but 0.05 minute inverse, because 1 by minutes, that is minute inverse, right? Now let us substitute that value of t equal to 5 in the expression of exit age distribution of the CSTR. So E of t for CSTR is equal to exponential of minus t minus tau p by tau CSTR, the whole divided by tau CSTR, right? Now let us substitute t equal to 5 minutes. We also know that tau is also equal to 5 minutes. Okay, so substituting both in the expression, we get exponential of minus of 5 minus 5 by tau CSTR whole divided by tau CSTR. So, which is nothing but exponential of 0 by tau CSTR. So, e power 0 is nothing but 1. So, 1 by tau CSTR is equal to 0.05. Because we know that e at time equal to 5 minutes is 0.05. So, this is equal to 0.05. That means your tau of CSTR is 1 divided by 0.05, that is equal to 20 minutes. Okay. So, now we have tau of the pipe, that is space time of the pipe, which is nothing but 5 minutes, and tau of CSTR 20 minutes. Right. So, tau of CSTR is volume of CSTR by volumetric flow rate, that is equal to 20 minutes. So, here, tau P by tau CSTR is equal to Vp by V naught divided by V CSTR by V naught. That is volume of the pipe divided by volumetric flow rate divided by volume of the CSTR divided by volumetric flow rate. Here the volumetric flow rate is the same because it is it is entering through the inlet pipe and then to the CSTR. That means with the same volumetric flow rate only, it is passing through the pipe and then to the CSTR. It is just an inlet pipe to the CSTR. So, we can cancel that V naught. So, that means tau P by tau CSTR is equal to Vp by V CSTR. Right? So, which is nothing but equal to 5 by 20, that is equal to 0.25. So, your volume of pipe to the volume of CSTR is 0.25. So, this is what is asked in the question. So, what is the ratio of volume of the pipe to the volume of CSTR? So, which is nothing but equal to your value of 0.25. Okay. Now, let's go on to the last question for this session. The convolution integral is relating the inlet and outlet concentration of the tracer is given by. So, we had there was a discussion on the convolution integral that correlates the inlet tracer concentration to the outlet tracer concentration. So, inlet we may have a pulse input or a step input, right? And there will be some outlet concentration of this tracer, from which only you will find out your exit age distribution and then f of t and then mean residence time, variance, standard deviation, skewness, everything. So, what is the relationship between this inlet and outlet concentration of the tracer? So, is it option A, concentration at the outlet is equal to integral over 0 to t C in t minus t prime into f of t prime dt prime, or is it concentration at the outlet is equal to integral 0 to t C inlet into t minus t prime, C inlet at t minus t prime into e of t prime into dt prime, or else is it C at outlet concentration, C outlet at t is equal to C inlet into t minus t prime into e of t prime, or is it D, C outlet at t is equal to C inlet at t minus t prime. So, what is the relationship? What is the relationship between the inlet and the outlet curve? Which of these is the correct relationship? So, the answer for this is, it is option B. It is concentration at the outlet at time t is equal to integral over 0 to t C in t minus t prime into e of t prime into dt prime. That means your output concentration will be inlet concentration that has entered the reactor before T of before T, right? Or T prime seconds, and then the exit age of that at T prime, sorry, it's not seconds, it's any time unit into exit age of age distribution of that at T prime time. Okay, this is what is the answer. So C at outlet the outlet concentration of this tracer C outlet is given by integral over 0 to T C in into T minus T prime into E of T prime dt prime. Okay, see all the tracer, you know, uh, at T entering the T prime before time T and then resides for time T prime. So will be in the outlet at time T. So whatever tracer has been into the reactor or a system or a vessel, right, before time T, and then which is having the residence time of T prime will be seen at the outlet concentration at time equal to T. This is what is the relationship. Okay. So that's it with the session. Thank you all.